Hey, how's it going? So now I'd like to answer this question: how does light bend? So we're looking at light as a stream of particles, as light rays, and we looked at these two analogies the last time. These two analogies were this energy conservation idea, where as a ball goes up a slope, because it's the forces that are slowing it down are perpendicular to the slope, are along this normal line here, it doesn't slow down on the y direction. It only slows down in the x direction. So if we know the speed before and the speed after, we can figure out this deflection angle here, theta d, and this is going to be larger if it slows down. We also asked a turtle what it would do if it wanted to go from one point to another point, and basically what it would do is it would swim to be fairly close to where it wanted to get off and to the point it wanted to get to, and then get on the shore and spend less time on the shore. Now, this wouldn't be the absolute minimum distance on shore, but it would be close to it. We found something very, very close to it. And these two models give sort of reciprocal answers, right? The sine of the angle of incidence is proportional to the ratio of the speeds, Vr over Vi, of the sine of the angle of reflection, or deflection in this case. In this case, it's the same idea. The sine of the angle of incidence is proportional to the sine of the angle of reflection times the ratio of the speeds, but it's actually inverse. Vi over Vr, the initial speed over the reflected speed, the incident speed over the reflected speed. It's the inverse of this one, which was Vr over Vi. So one of these may be true and one of them may be false. Obviously, something else might happen. I'll talk about the principles that we actually care about in this case. Not too terribly much, but a little bit. And we'll decide which one of these ideas works, and we'll end up with Snell's law. So what we're going to end up basically doing is modifying Hero's principle. Now, Hero was a Greek philosopher. They didn't really have physicists back then, and he surmised that a beam of light that goes between 2 points, say from this object to your eye, that hits a mirror will take the path of least distance, or the smallest distance path. Rather, like if it goes in a straight line, it will do the same thing. And this is one way to think about it, right? When you look at an object in a mirror, when you look at this guy in the mirror, what you actually see, it looks like the object was just reflected, like you took a piece of paper and folded it in two, and this is, and you end up with this guy meeting this guy. So this straight line is what's going to be the least distance, just like it would be the least distance of all the possible paths that intersect this mirror. So a longer path means a longer time. So if this guy was coming down here to hit and come down here, it would be a longer path than if it just went in a straight line here. So for the same reason, basically, that light travels in a straight line in space between 2 points, when it reflects off of a mirror, it has the same angle, the reflected angle, as it does of an incident angle. Hopefully that's fairly simple. I mean, it's something I think we all understand fairly readily. It's something you can do at home. All you need is a light, possibly a piece of cardboard with a little hole cut in it, and a mirror in your bathroom, and you can probably do this experiment. Okay. So Hero's principle could either be the least distance or the least or the shortest time, because basically they're the same thing, right? If you only have one speed, then the shortest distance is the shortest time. Fermat's principle, which came a few centuries later, probably 13 or so, maybe more. I should have looked that up before I decided to open my mouth, right? Here, that's going to say that path taken between 2 points by a ray of light is the one that traverses in the least time. So we've already seen that that was our turtle. So Fermat says the turtle problem is the one that works for optics, and that's really a matter of scientific investigation. That's a matter for experiment. People already knew that if you shined a light from air, which has a smaller index of refraction than, say, glass or water, it would move like this. So it would bend, and you'd get a shallower angle. So you need a theory that accounts for that. And it turns out that it's it turns out that Fermat's principle says it's the principle of least time that accounts for that. So in that case, we have a slightly different thing going on here, which is that because the index of refraction is c over v, and if we go back here, this is inversely proportional to v, which means that this 1 over v is going to be equal to n over c. C is common in both sides, so you get this thing here at the bottom. This is Snell's law. The index of refraction in one material times the sine of the incident angle is equal to the index of refraction of the second material, the blue part, times the sine of this refracted angle. It's fairly useful. I should have an example about fishes. There usually are. Usually when you do this, you have a nice example about a fish. So that's perfectly reasonable. You're good with that, I hope. It's not that difficult a concept. So here we have a simple problem. This is the one you'd see in a lab or something. And the reason why you have this circular pendulum, this semicircular pendulum, or I shouldn't say it's a pendulum, it's a lens, semicircular lens, is because at this point, if you shine your beam right at the center of this lens, then when it turns, this line here will be along a radius. And therefore, because this is semicircular, it'll go out directly perpendicular to the face, or directly normal to the edge of the glass over here, and then you can have something over here to measure how far the thing's gone, right? Or how much, what this angle actually is. So that's the only reason for having this sort of semicircular lens. We have all of the things we need to really know about this, and we want to figure out if this angle theta I is 45 degrees. Here we've got the index of refraction of air, which is going to be close enough to 1 if it's going into something like glass, which has an index of refraction of 1.5. That slight deviation from 1 that air has is not really meaningful. Then we can, do a little bit of math. So we want to figure out what this refracted angle is, because we know these other three quantities. So we just sort of fill them in. So we say 1 being this index of refraction here, times sine 45, which is this incident angle, is 1 over the square root of 2. But it's also equal to, from Snell's law, 1.5, this index of refraction of the glass, times the sine of the refracted angle. So another way to look at that is we have 1.5, or 3 halves, times sine theta is equal to 1 over the square root of 2. We multiply each side by 2/3. 2/3 times 1.5 is 1, so we have sine theta here. 2/3 times 1 over the square root of 2, which is this, is equal to the square root of 2 over 3. That's less than 1, which is good because this sine theta is always between -1 and 1, so this number here had better be less than 1 and greater than -1. Basically, it also has to be greater than 0 because it's not going to come backwards. This theta can't be greater than 90 degrees. Definitely can't be greater than the 180 degrees that makes it negative. So if we have that, we just take the arc sine, we take the inverse sine of the square root of 2 over 3, and that gives us 28.1 degrees. Simple enough, you should be able to do that kind of problem. All right. So what have we seen in these 3 videos, I think, at this point? We've seen that photons move in a straight line at the speed of light unless they're in a material, at which point by this absorption and re-emission process they slow down. You measure how much they've slowed down by the index of refraction, which is the ratio of c, the speed of light in vacuum, to the speed of light in the material, which means that this is actually how much faster the light would be in vacuum than it is in the material you're looking at. And this number has to be greater than 1. Fairly nice. So we've seen that. And the only other thing we've really seen here, after all this talking, is that when light bends as it enters a material, it follows Snell's law, which is the index of refraction times the sine of the angle of incidence is equal to the index of refraction of the new material times the sine of the angle of refraction. Something you should be able to use, do lots of fun things with it, and maybe even talk to people about it at parties, because that's what people like to talk about, is Snell's law. I should say that at the dentist today, while I was sitting in the chair having everybody ignore me, people were talking about physics in the next room. It was actually kind of neat. People were talking about quantum entanglement. I'm pretty sure they were getting everything wrong. I think they probably got what they knew about quantum entanglement from watching Ant-Man and the Wasp. But people were talking about physics in the next room. So you should start talking to people about physics in random situations, especially parties, especially when everybody's drunk and nobody knows what they're talking about. So I will sign off there, and I will talk to you next time. Bye now.